In this video, I want to introduce forces and give you some examples and talk about something called Newton's first law. So up to now, we've talked about kinematic equations. Kinematic equations, remember, relate position, velocity, and acceleration variables. This is what you need to do if you want to explain motion. You explain motion by giving the position, the velocity, and the acceleration. Okay, that is enough to tell you how something moves. Alright, now what about if you wanted to know why something moves? Why does something have whatever acceleration, or why does it have a certain velocity? Why does it have that position? Okay, so we're going to kind of dig a little deeper now and think about why things have the kinematic equations that they do. Alright, and what's going to happen is that a lot of motion is going to be explained by pushes and pulls. Something somewhere is pushing and pulling on stuff. Okay, now we have another name for pushes and pulls. We call those forces. All right, it's nothing more than a push and a pull. All right, now you don't need a push or a pull in order for something to keep moving. That's an interesting observation. For example, think about a asteroid moving through space. Okay, it'll move through space in a straight line forever and ever, even though there's nothing pushing on it or pulling it, right? Okay, another example is, think about if you've ever played air hockey or ice hockey. Okay, you have a puck, and if you hit the puck, it almost seems like it'll slowly keep moving forever and ever, right? Now eventually it'll hit a wall and the ground is not perfectly smooth, but if everything was perfect and infinitely long, that puck would just go forever and ever, just like the asteroid through space. Okay, so those are two examples where to show that you don't always need a force. Okay, so what do we need a force for? Okay, we need forces whenever we want to change velocity. Okay, so that's interesting. The examples that I just gave you where you didn't need a push or a pull, they all involved something moving at a constant velocity. Okay, you need a push or a pull to change a velocity, and we have a name for that. When you're changing the velocity, that means you have an acceleration. So it's acceleration that requires a push or a pull, that requires a force. Okay, now why do we need to push and pull in order to get an acceleration? Well, objects just don't like acceleration. They fight you. Literally, they fight you. Let me show you what I mean by that. Okay, take a pencil or a pen in your hand. Okay, and I want you to move it back and forth really fast, back and forth, back and forth, back and forth. Okay, now you are changing the velocity. How are you changing the velocity? Well, in one instant you're moving in one direction, then you're forcing your pen or pencil to go in the opposite direction, and then you keep repeating that, right? You're also, as you change direction, you're decelerating and then accelerating. Okay, so there's lots of velocity changes going on there. Okay, now that takes a certain amount of effort, doesn't it? You have to literally push or pull. Okay, now I want you to do the same thing with a big textbook. Take a Bible or your physics book, take some big beefy textbook in your hand, and I want you to move it back and forth at the exact same speed as the pen or pencil. Okay, really fast. Okay, try that now. Fast, really fast. Okay, I think if you tried that, I think you would agree that the textbook was a lot harder. So if you didn't see the resistance to acceleration in the small mass object, you certainly saw it in the big mass, the textbook, right? Now, if you want an even more dramatic example, try putting your car in neutral and try pushing it down the street. That's going to be even harder to do to get an acceleration, right? Okay, so we have a name for this resistance that objects have to acceleration. It's called inertia. Okay, inertia This is the the property of objects to resist acceleration. They just don't like it. Okay? Now, not only do they not like you speeding things up, they also don't like you slowing things down. Remember when I talked about the car being very difficult to get moving in neutral? Okay, think about the opposite problem. Let's suppose you got 3 friends, they all push the car. So now you got the car going down the street at a nice, decent clip. Now, all of a sudden, oh my God, a squirrel just ran in the middle of the street. Now I want you to make the car, quickly come to a stop. Okay? That's not going to be easy, is it? You're going to need your 3 buddies all over again, pushing all of them together to get that dumb car to stop. See? So even decreasing velocity is really hard. Okay? So inertia always comes in when you are changing the velocity, whether up or down, doesn't matter. Okay? Now, you saw that the car in the textbook had more inertia than the pen or pencil, so you can also add this note to your inertia definition. The amount of resistance, the amount of inertia, depends on the amount of mass. So more mass means more inertia. Okay? Now, if you want some more experience with inertia, I've got a little side note for you. So it turns out that in the future, when we all navigate through outer space, we're not going to be able to drive a spaceship the way that we drive a car. Okay? Now, why is that? It's because of this stupid property of inertia. Okay, it's just too difficult to deal with, especially in 3 dimensions. Okay, I'd like you to try the following. I want you to do a internet search, a Google search for PhET lunar lander. It's a little game. It's a little simulation that simulates the Apollo 11, the little craft that landed on the moon using little rockets. Okay, I want you to try that. You'll see how difficult it is to navigate a spaceship to land on the moon. All right, try that now. That'll give you another experience of inertia and how annoying it is to keep having that resistance to changes in velocity. Okay? Now let me continue talking about forces. Okay? The units of forces are newtons. This is in honor of a famous scientist named Isaac Newton who studied forces. All right, so like you could say the push, or he pushed the car with a 5 Newton force. Okay, you could say stuff like that, where capital N is the abbreviation. All right, or how about something like, gravity pulls on objects or pulls on a rock with a 10 Newton force. That would be maybe another example you might hear somebody say. Okay. All right. Forces are vectors. That means that they have length and direction. Okay. You know that that makes sense. If you push something, if I push a car, it makes a difference whether I push it with the strength that I push it with. Certainly. Okay. A big push is different than a little push, but also the direction matters. If I push your car to the gas station to get more gas because you ran out of gas, that's not the same as if I pushed it in the opposite direction to cause trouble. Okay, so strength or length and direction are both matter for forces. Okay, now what happens if you have multiple forces? Okay, you can the total force from multiple forces is the vector sum of all the forces. So what does that mean? You have to find the components, you have to pay attention to direction, and once you have the components, only then can you add the forces together. Okay? Let me show you how direction matters. All right? Suppose you had two people pushing a car in the same direction. That means they would add up and you get a big push in one direction, right? Now, suppose instead you had one person on one side of the car, let's say on the front, and then you had the second person on the back, and they're both pushing in opposite directions. They're both fighting each other. That would be a lot like a tug of war, wouldn't it? Okay? When they're fighting each other tug of war style, the sum is a small number. It might even be 0. Okay, so the total force could be 0 when you can have two big forces in a tug of war. You can have two football teams, both evenly matched, pushing in opposite directions, and you add them together, and the net force is 0 newtons, and that's why the rope doesn't go anywhere. Okay. All right. So total force, you do a vector sum, and then let me close by mentioning what is called Newton's first law. Oh, but before I show you Newton's first law, let me give you some other examples of forces in the real world. Okay, so you can certainly have people pushing or pulling. Let's see, what else can we say? Gravity. Okay, gravity pushes everything down or towards the center of the earth. That's certainly an example. Magnetic forces, magnetism. We've all played with magnets before. Later on you'll learn that there's also electrical forces. Friction. Okay, you can have, like if you slide into second base in baseball, you can have friction. You can also have air friction. Like when you're riding a bike, the air friction slows you down. That's another example. You can have spring forces. Okay, we've all played with springs. If you compress a spring, it resists you. It doesn't want you to compress it more. If you stretch it, it doesn't want you to stretch it more, so it tries to pull it back to the right size, the original size. Okay, so these are all examples of some forces. Let's see, what are some other forces that you might see? We got gravity, magnetism, electrical, friction, springs. How about this? Right now you're probably sitting or standing, okay? Now, is gravity operating on your body? I hope you'll say yes. You're always being pulled down every second of your life. I doubt any of you have been to outer space. Okay? Now, why if gravity is pulling you towards the center of the earth, why aren't you falling at high velocity towards the center of the earth? Well, that's because the ground is pushing up, isn't it? There's the total force. If you're not moving right now, the total force on your body is 0 because the gravity's pulling down, and there's an equal strength force either on your seat if you're sitting or on the floor if you're standing, pushing up. Okay, that force that doesn't let you move through objects. Okay, the same thing you would experience something similar if you tried to walk through a wall, right? The wall you're gonna bonk your head. The wall, solids don't let you move through them. They resist you. Okay, so this is what I want to focus on. This force is called the normal force. Let me just first of all write the name down. Now, normal, why do we call it the normal force? Normal refers to the direction. Normal means perpendicular. So this is really like saying the perpendicular force. If I have a surface, okay, let me make a purple surface, and if I put a box on that surface, let me see if I can draw a box. Okay, so you have gravity straight down. So I'll draw a little arrow to represent gravity. And then the normal force is perpendicular, or in other words, normal to the ground, normal to the surface. So that is straight up like that. All right, let's do a wall now. If I had a wall over here, okay, and let's say now I have a ladder leaning against the wall. Okay, now as the ladder leans against the wall, there is a normal, well actually in this case, interestingly enough, there's two normal forces. You have the ground pushing straight up, in other words perpendicular to the ground, normal to the ground. So that's the normal force due to the ground, but you also have a force perpendicular to the wall. Okay, so let me draw that arrow, and the ladder experiences that on the other end. Okay, so every time you have a solid surface, you have a force perpendicular to the surface, normal to the surface if something tries to press into it. Okay, with that said, now that I've defined total force as the vector sum, let me close by giving you what's called Newton's first law. And this is really nothing new. It's just a restatement of what I said about inertia. Okay? So here we go. Newton's first law, and it's also called the law of inertia. And there's a couple different ways of saying, we've already talked about this, I'll say to try a couple different attacks at it, but objects have a constant velocity unless a net force acts upon them. All right. Net is another word for total. So in other words, if you add all the forces on an object, if it adds up the vector sum, if it gives you a total force or a net force that's not zero, then only then can you have an acceleration. Otherwise, if there's no total force, there's no acceleration. All right, that's what Newton's first law tells us. All right, so I mean, we can try different ways. I don't know what will click with you, but we might also say no total force means no acceleration. Okay, so both of those are basically saying the same thing. All right, that's Newton's first law. And why is that the case? Well, inertia keeps inertia. You can all the things we talked about inertia. Think about that to explain why things move with a constant velocity unless there's a net force, a total force acting on them. All right.